hole?
The shell is probably about 4 years old, but it's got several hard drives.
So it would be a combination. How are you? Yes. Probably the best one would be Hess. If you see a access point called Hess, that would be the one in this room. Password is Mars or bust. All lowercase, no spaces. Thank you.
Do you want to bring it up on here, Ryan?
Yeah. You want me to? You ready? I'm sorry. Yeah, I can drive them back here. Doesn't matter.
I'll just type it in.
Okay. Did the links not work through the website there?
It's just not live yet.
Oh, okay.
The feed's not live.
Oh, okay.
I'll have it go live at like 1:15.
Oh, okay.
Let's start at 1:30.
Such a wonder.
Hang it.
So yeah, I am broadcasting a camera shot to Ustream. There you are. Wait 10 seconds. Okay, I'm done. Good.
Oh, that helps.
Actually, I'll take a shot at this thing. Actually, I kind of moved it over a bit, but it depends on where they sit. If they sit closer to the center of the table, I think it'll be all right. Otherwise, if you could scoot a little bit more to the left, I'm not sure how close.
The only thing is I need connections.
Yeah, yeah, you can plug into that UPS there. This, yeah, you can plug it.
Well, I mean, you want to read them?
Yeah, why don't you just go ahead and read it at the end, just for caption everything, you can send it, but,
Yeah.
kind of everything. Yeah, you don't mind doing that.
Check it over here.
Okay, so here we go. When they sit, when they sit down, it gets a little bit more light.
Wow, what a laugh.
Yeah, yeah, it is.
I'm like, I'm not doing that.
Yeah, it's really confusing to watch.
Well.
It's like you're going to another planet.
Yeah.
Yes, this is, I'm still seeing much.
Yeah. What time do it?
Wow.
Will that shorten the delay?
Yeah, I can't move until you move the table.
Sorry.
I'll move a little bit. Did you move the table? Oh, nice.
It's loaded.
What if you turn them? Yeah. Maybe the other way. We're not going to catch it on the camera then. That's okay, we don't need to have our names now. It's just, I think it's just right where that light is. Those can lights, but if you bring up the front ones.
Oh, yeah, you can turn those off.
Yeah.
Or you can turn the fluorescents off and just leave the light. Is that exam?
That's better.
That. Do that kind of Google profile.
Yes. Yes, yeah, that's right. Well, if you go to brown and.
Here?
Oh, that's right. The guy was there. Open season.
Yeah, that's right. You want to get back on the podium with that? Right, I'll go ahead. Yeah, all these outlets around the perimeter, yeah, I don't know if you want data sharing for right here or that's going to be Q&A line there, so might not be a good thing to. If you want power, it might be best to come back here.
I'll work too.
I'll see how long I go before I need it.
Yeah. Yeah.
Just up in all evening.
Okay.
Was not invited.
Here we are.
I think it's, we want to have all the ideas put up.
Hey, Brian, how are you?
Yes, sir.
That's out of the room.
So that's the combination.
Oh, okay. Yeah, I will, Brian. I'll point him out when he comes in the room. Josh, it's Brian was looking for you. Hi.
All right, actually, what did you talk?
Yes.
And I hope I didn't do injustice to the facts.
No.
Anything I saw for you.
Yeah, no, actually, yeah.
Yeah, because the thing that is driving stuff that we feel a need to not that is, if we touch it and it comes apart, we have to
Right.
matching the instantaneous velocity. If it comes apart in the bag,
inserted that, was that in the original science
Right.
objectives?
Right, that could
Build
damn
that.
voucher.
Oh, from,
Right, yeah.
discovered it,
Yeah,
right.
Okay.
That's their
Oh,
uniform.
yeah.
The Osiris has security.
So, anyway, so we, went over all the concepts there, and we would assume that it won't come apart for too much.
So we're still working on that.
Well, yeah, I mean, they won't be so robust.
Yeah.
It is.
It might actually be hard to do something.
Right. Well, right, there's a worst case from a, basically, conservation manual. The best case would be to have a lot of damping. And
Right.
the worst case, because a lot of that, you might have become a single spinner.
Yeah, but you also.
Yeah.
Yeah.
Yeah, although velocity, someone pointed out these velocity.
Right. Velocities are tight, so the energy.
Poke a hole in Vectran takes a,
Okay.
on the, on the Pathfinder, they had to go to a 4-ply Vectran.
Okay.
Because they were coming down, like
But
a
I
rock
guess-
10-story building. And we
You
hit a
know,
sharp
okay,
rock.
so probably below 3,
That's an issue.
well, hard
Yeah,
hard
yeah,
code
you
is
sort of
good.
bump it up, you know.
Well, that's, you get to the
Yeah.
point where you're beyond the visual.
A light kiss by comparison. Thanks for talking.
Yeah, yeah.
But not, you can't be up there.
Right.
All right. Okay, got it. All right, all right.
We have two solutions for the density and thermal inertia. One solution looks like monolith covered with fluff. And the other solution looks like highly porous.
Yeah, right.
I think that solution doesn't quite solve it. We're still these parameters here. A lot of that.
Because you have a lot of exposed monoliths held together with, a lot of fluff. Do you high thermal inertia and low density?
Yes, there was a topic to have this like when you site over.
Kind of held together with Vander Waals.
Except that you violate size distribution.
That's true.
You don't find a collection of similar size slides without all the little stuff.
Ah, true.
On the other hand, the one opens.
Yeah.
You could easily argue that all the little stuff got swept away by.
Okay.
So that's just an update.
When do you think
on
you're
the-
gonna publish?
On the QT, because there's still sorting things out. We're having to sort of complicate once we try to reconcile everything.
When will you be sure of that?
You have it, manuscript in your hands.
All right.
Otherwise, you didn't hear from me.
All right.
Yeah, we did.
I'm just saying, that's not always the case, but there's something like that. It's some generic. Over on that side. Yeah.
The rest of the thing is,
Yep. Much hardware is now going. True.
In subsequent, it sounds like well, it's all about how good the rush is. It's all about guidance, right? So you can always but
Your farms actually material station, are hijacked and they are art proof. Really what's going on? I'm doing fine.
a cartoon with
I have plenty of
just wanted to see if you have any ideas about this. Yeah, I'm trying to. So this is my idea of how to organize a thermal inertia where you have lunar regolith, gravel, and then porosity, you've got monolith. In the middle, you have your ordinary this axis is kind of a homogeneous line where it's fluffy from center to skin, right? It's got low high porosity and low thermal inertia. And then this is the other homogeneous. You have this kind of continuum here. And then off the axis, you've got this hot, you've got thermal inertia bare rock, and high porosity, which looks not good. Right. Although somebody proposed but that's still going to have this low conductivity. Pumice is not the bare rock. There was a suggestion that what you could have is a collection of one-size My objection to that is
you have
everything in the
not
at the maximum possible. So how do you get it?
Your life was
completely up in.
Yeah, but who's there speaking to the
All right. Good afternoon, and I'd like to welcome everybody to the Asteroid Deflections demonstration session here at LPI. What I want to do is, first of all, to acknowledge the session chairs, introduce myself. I'm Dan Masnick. I'm a senior space systems engineer at NASA Langley Research Center. I was one of the members of the Keck-sponsored study on the asteroid retrieval mission, and I'm currently leading the efforts for the agency on looking at the alternate approach for the asteroid redirect robotic mission. My session co-chair, Pat Troutman, is not present today. He had some family matters that he had to attend to. He will be joining us virtually, and Pat, he leads strategic systems analysis activities for HEOMD back at Langley, the Human Exploration and Operations Mission Directorate. To my left is Paul Abel, who is ably providing cover for me, and I appreciate his help. Paul serves as in the Astro Materials Research and Exploration Science Directorate at NASA Johnson Space Center, and is a leader in small-body planetary science. So I'll mention again for the folks online, you know, you can go to www.nasa.gov Asteroid Workshop, and you can join in the discussion and send questions to on Twitter at #ProtectPlanet. What I'd like to do is, first of all, just kind of give a little bit of background on this session. So next slide, please. So the purpose of this session is to look at deflection techniques that could be applied to bodies or objects that are large enough to provide or to result in a significant damage if they were to impact the Earth. Roughly, we're talking about something in the 100-meter or larger size. And the RFI call was looking at demonstrations in these various areas that are up here, but not necessarily limited to those. So that's what came out in the RFI. Looking at slow push techniques. In particular, one of those that was called out was the gravity tractor technique. Also looking at ARV instrumentation for investigations that are useful to planetary defense. The use of deployables from the ARV to demonstrate techniques, again, useful. For example, a standalone transponder for continually tracking, things like that. So everything from the actual devices that would invoke or impart the delta V on the object to secondary supporting equipment. Let me just say, you know, we've kind of echoing off Chris Moore's comments from last night. You know, we've spent 4.5 billion years here as a planet, kind of sucking up asteroids and comets and taking the shots. And what's interesting now is we're finally starting to talk about how we could kind of come back at them a little bit here, prevent them from doing that in the future. I think that's really exciting, and I think that's an important part, potentially an important part of this mission. So the next slide. We went through, we had 92 responses in this session, and we've selected 13 responses in the categories below. They're basically kind of grouped into 7 basic areas. This was, you know, repositioning a small asteroid or portion of an asteroid to impact a larger asteroid, kind of the cosmic billiards approach. And we'll hear a couple presentations on that. You know, we're already demonstrating moving a large class of mass, but this potentially is a great planetary defense technique in the future that we look at. Using the high efficiency engine thrust to push a rotating asteroid while using the opposing thrust to hold relative position. This ion beam deflection approach. We're going to hear some talks about that. Kinetic impactor is still a viable approach. Maybe the most viable depending on warning time, and we'll hear a couple talks about that. One of the areas that's been talked about quite a bit is this enhanced gravity tractoring with local mass augmentation, and we'll hear about that. We've also looking at using the sun's energy to vaporize the material, and also looking at swarms of small satellites to attach and despin and redirect. And finally, we had an area 7 that looked at technologies and approaches that are applicable across the entire mission our different non-deflection topics that are related. So just quickly, I'm going to go through the agenda and the little logistics here. Next slide, please. We're basically going to have a first series of presentations. Go ahead to the next. I won't go through them all. We'll take a short break. And the way we've got it structured, since we've revamped the schedule here for this, the extended portions of the workshop, is we've got 2 hours set aside for tomorrow morning from 8 to 10 over in the Berkner room. And we're going to have a short discussion, what I call the initial discussion and synthesis this afternoon. Based on what we've heard today, in the morning I'll have some slides that will kind of massage and discuss in real time in preparation for the plenary session at 10 o'clock tomorrow. So I hope folks can join. If you can't join tomorrow morning at 8, certainly we'll have about roughly 25 minutes to discuss things this afternoon before we have to adjourn. What I'm going to do is I've asked each of the presenters to keep their talks to approximately 13 minutes, give a couple minutes for question and answers after each presentation, which is a little bit of a change from the last time. I think that'll flow better. We're going to stay on time. If we get a little bit ahead, like we did for the capture session this morning, we'll take a brief break just so if folks are coming in to hear a particular talk, we can be as close to time as possible. We've got several folks that will be presenting virtually, and we'll cue them in. And for the virtual presenters, there'll be a time clock that they can see. For everybody in the room, we'll give you a 3-minute warning. So at 10 minutes, I'll hold up a 3, and we'll go from there. So I think we've actually got a couple minutes in order to stay on time. I think if there's anything else I wanted to say. Oh, I guess to fill in, I can say from the responses that were provided, we had the guidance of the relevance, the impact, the maturity, and the affordability. Some of that's kind of in the eye of the beholder. Some of these concepts will probably add some cost to the Asteroid redirect robotic mission. But we wanted to hear the ideas and see how we could incorporate those. Some of the ideas will probably be lower cost, and obviously some have more near-term applicability. But we tried to select those from the 92 that were submitted to try to keep in the near-term technology development, something that we could fly if we had the proper funding at this time. So with that, why don't we go ahead and get started? We're pretty much on time. Our first presenter is Mike Elsperman, and he's actually filling in for David Smith, who was on the agenda originally. Mike is a director of space science and advanced space utilization for Boeing Phantom Works organization. He's chartered to develop and mature innovative space technologies and capabilities, create new space market opportunities, and enable business creation and growth. So I'll hand it over to Mike, and welcome.
Thank you very much. Good afternoon, everybody. Nice to be here to talk about this topic. I want to give upfront credit to Dave Smith. He works in my department. He's an ex-JPLer, so you can rely on him. Probably might be known. Dave does a lot of research on this concept, and I'm going to do my best to try to represent it today. If there's questions I can't answer, I know we can take actions and we can do that. The basic concept that we explored with this response was, can a large geocom-derived asteroid redirection vehicle be used to do demonstration of initial deflection methods? We looked really at 4 possible methods to include on the mission. One is called ion beam shepherding, using the same thrusters as developed for the redirect mission for the propulsive capability, basically put on the other end of the space vehicle and use it as a candidate to bombard the asteroid with ions and create a slow push, low thrust force there. The gravity tracker concept, everybody's pretty familiar with. If you've got a massive enough spacecraft to do actually the deflection of the trajectory. The local mass augmentation, whenever it really does have that, would obviously probably help. And then direct push, actually going down and touching the asteroid and pushing it, which effectively is what the capture system does, the management factor. There's some work that's required there in order to ensure the impact hits the asteroid. But those are really the four methods that we look So a little bit on the Asteroid redirect vehicle concept that we came up with. For the first part of the RFI, we proposed a commercial spacecraft derivative as the point of departure for the redirect vehicle. Boeing has a large product portfolio of spacecraft. The one in particular that we looked at was the 702 MP, which is medium power.
Hey, Mike, sorry to
Sure.
stop you real quick. They're apparently having trouble hearing you online.
Okay, try that now.
Is that better?
Whoa.
Loud. I can speak softer now, I guess.
Okay, there you go.
That's better. Okay, I'm sorry. The ARM vehicle that we developed a design for the first part of the RFI response was based on the 702 MP. Roughly, we came up with a design that weighed about 14,700 kilograms, roughly a 10,000 kilogram xenon propellant load, based on the assumptions at the time of about a 1,000 metric ton asteroid. Also, working with the JPL design team, at the time the concept, we came up with the LRO injection delta V was about 60 meters per second, which really kind of drove a lot of the propellant load. Subsequent to that, Dave talked with some of the folks on the team that the 2009 BD mass was assumed to be a little bit less than that, maybe 50 metric tons. At least that's the assumption we had. Not sure what it is today, but that's the assumption we used for this. And also the insertion trajectory got refined such as the delta V requirements were less than, as you do an iteration, I think it's going to get more detailed, more refined. So a lot less. So the spacecraft overall size came down around 6 metric tons. So the question that we posed is, can you do an effective deflection demonstration with a 6 metric ton asteroid redirect vehicle? Some of the four methods that we've talked about, we've kind of eliminated two. The direct push, once again, the capture mission really accomplishes that, so we didn't look at doing any mods to that. The kinetic impactor method, that would require some additional hardware, and this kind of, we thought it was a harder implementation. So for our first pass, we focused on ion beam shepherding and the gravity tractor approaches. So for the EP thrusters that are being considered for the mission, I've shown a couple here from our friends at Busick and Aerojet. We've been working with them closely for quite some time on solar electric propulsion demonstration missions and other technology development activities. Busick they currently have two thrusters of 8 kilowatts and 20 kilowatts that are in mid-TRL level. Probably some still work to do on those, but they are beginning to develop a 10 kilowatt thruster. That's derived off the 8 kilowatt thruster they have currently. And then Aerojet has a 12 kilowatt thruster with the performance specs there. So there are some relatively mature technologies in terms of high power thrusters that will be useful for the redirect mission. These would also be used for the ion beam shepherding activity, where you would actually blast the asteroid, if you will, with the ion beam coming from the thrusters. Dave, in his work, went out and did some research and found some very, recent papers by a gentleman named Claudio Bombardelli, who has done extensive work, it looks like, to come up with an analytical approach to determine the effectiveness of both the ion beam shepherding and the gravity tractor methods, and gives a relative comparison of them as a function of the effectiveness of each technique in terms of maneuvering, making the asteroid deflect. So his chart there shows, for his initial data line, he assumed a spacecraft that had an inverse specific power of 5 kilograms per kilowatt. That's for probably a very lightweight custom spacecraft that generates a lot of power. For the point of departure for our vehicle, we're around 20 kilograms per kilowatt, so it's not quite as efficient. But since you still have a lot of power and you have a lot of mass, relatively speaking, we think it would be a good platform to explore doing these demonstration missions in tandem with one another. So we assumed a delta time to do the deflection demonstration of about 2 years. For the IBS demonstration, about 2 asteroid diameters hovering away from the target, and for the gravity tractor, Bombardelli assumed 1.5 asteroid diameters. So for the ion beam shepherding technique, Bombardelli created this curve, or these set of curves, as a function of the spacecraft mass. His work assumed a 150 meter diameter asteroid. So in our analysis, we were assuming that we'd be doing the demonstration on 2009 BD, which was the notional target at the time, which is much smaller. I think it's on the order of 10 meters in diameter assumed. So our spacecraft fits on the curve where the red dot is. So you can see that, and what these represent is for a given mass of a spacecraft, for a given force, the amount of time it would take to move the asteroid out of its trajectory by about a distance of 2 Earth radii. And mass of IBS is the mass of the spacecraft. Obviously, Lower mass spacecrafts, according to the analytical approach that Bombardelli produced here, is that they're more efficient at the same specific power. So our inverse specific power for the Boeing ARV is a little bit higher, so it's not going to be quite as efficient. However, we think that in about 2 years, you could probably get maybe a 3,000 kilometer deflection by using the ion beam shepherding method with one of the thrusters that we show. So you wouldn't get the full two Earth radii deflection that Bombardelli would assume, but you could probably measure that change in trajectory pretty well. So for the gravity tractor application, we think that even with a 6 metric ton spacecraft in interacting with an asteroid about the size of 2009 BD, you could see also a significant trajectory deflection. For the curve shown here, this is a function of the mass of the spacecraft and for different forcing function, different forces applied. Our asteroid redirect vehicle kind of corresponds over on the left-hand side there. Once again, assuming a 1.5 diameter asteroid diameter hover distance. A deflection force based on gravity alone of about 0.1 Newton over a period of time, about 6 months. We think it would, we can calculate it would give you about a 1.25 meter per second change in velocity, which should be measurable by conventional Doppler tracking methods. Obviously, a larger spacecraft would probably have a higher, more efficient, you'd have a larger deflection. Also assume, once again, this data is based on 150 meter asteroid diameter. We might be able to do better than that. We might be able to do a more significant change given the fact that it's a smaller target. So in conclusion, we think that for the redirect mission spacecraft that we developed for the response, you could do 2 deflection demonstrations on a single mission. You would do the gravity tractor first, then followed by the ion beam shepherding. Once again, the 6.1 metric ton spacecraft that we're assuming here is based on would give the deflection to the 2009 BD target. Once again, we're not sure where we're going to go, or there's some uncertainty on the 2009 BD mass as well. The propellant load for the deflection mission would be enough to do the ion beam shepherding demonstration. With that small of a spacecraft, though, you probably couldn't do the deflection demonstrations and the redirect mission on the same vehicle. However, if you did go up to the full-size spacecraft to the full 10,000 kilogram propellant load, if you wanted to load it up full, and you wanted to take the extra time required to do it, you could probably demonstrate those techniques and still do the redirect mission, bring the target back to lunar retrograde orbit as well. So we think this would be 2 good demonstrations to put on the mission for sure.
Okay.
And that's it.
All right. Thanks, Mike. We've got about 4 minutes for questions. So, any folks that would like to?
Sure, Josh. Go ahead.
Grab a microphone just so everybody can hear.
So I apologize if I was supposed to figure this out from one of the graphs you showed. I was having a little bit of trouble figuring out the dimensions. But can you talk a little bit about the efficiency of the impulse imparted on the asteroid, given that the beam of ions coming out of the thruster diverges quite a bit?
Yeah, I think in Bombardelli's paper, he assumed a 74% efficiency. If you did some work on being able to reduce the dispersion angle on the thruster and get it more focused, I'm sure you'd have more efficient, you have more thrust imparted on the asteroid. But he took into account in the curves there that you're going to have some type of a beam diffusion that's not going to be absolutely, all imparted on the asteroid. Does that make sense?
Yeah, I'm mentally processing. That seems a lot higher efficiency than I would have guessed, but I guess that's probably because even though the beam diverges a lot, that there's a lot more particles in the center of the beam than in the outside. I don't know.
That out of my knowledge range. I can check it for you. I can tell you what I would love to do is I can give you a reference to Bombardelli's paper that might provide that to everybody.
Yeah, I think that's what basically the case is there. It's the distribution, so you're getting
And you could also vary the hovering distance too if you wanted to get closer, but then you've got to worry about maybe blowback on the spacecraft and things of that nature.
Do other folks have questions? And actually, John Brophy just stepped in the room. He might have been able to answer that question in terms of efficiency.
Timing is everything, John.
Just say yes.
Yes.
There you go.
So I had a question about the rotation of this of the target. You're talking about putting a spacecraft that's going to be, what was it,
if I
Couple,
remember,
couple
2 meters,
diameters,
right?
A couple diameters, asteroid diameters.
Diameters,
So,
okay.
yeah,
So if it's a 10-meter asteroid, you might be 20 meters away.
something like it, yeah.
That's true for the gravity tractor as
The
well?
gravity tractor was 2 diameters, and the ion beam shepherding is about a diameter and a half. So you're a little
Diameter and
closer.
a half.
Was it the other way?
He said other way around. Yeah. But I mean, so okay, so that's the scale. So you're not that close, but it still seems like some of your thrust might be going into rotating the body or despinning it, as opposed to just a net thrust. And I just wonder if that might have.
That's a good question. I don't think we considered the effect on the rotation of the.
I mean, because they're not
of the
spheres,
target.
right? They're going to look like
Yeah, they're
potatoes or
weird
something.
Shape, yeah, weird shape.
And so you could easily be spinning it or unspinning it or whatever.
That's a good point. So in the first pass analysis here, we didn't look at the effect on rotation. I think we assumed that you were just going to have, all the ions were going to impart all their momentum on the asteroid, assuming it was flat, not moving, not rotating. So maybe some less efficiency.
Yeah, I think you're going to lose some efficiency there.
That's a good point. That's a very good point.
Do you have any questions online at this point?
Okay.
Anything else in the room? I guess maybe I'll ask a question
Sure.
here in terms of you focused all this on the smaller target. You didn't look at any of the larger effects on the larger one.
No,
We'll
but
see some other presentations.
That did it, yeah. So if you were going to go and do that, I think if the boulder plucking technique is where we actually go, you would still do a deflection demonstration. It might be harder to determine the actual effect of the techniques on the larger asteroid. Once again, if it's much bigger, that's just a function of the way you would really see the change in trajectory would be the amount of time that you're actually doing the deflection demonstration. I think the mass would take more time to see a discernible change in the trajectory.
Okay. All right. Well,
Okay.
thanks.
No problem.
We're just a minute or two ahead here.
Dan, I
All
can't
right,
seem to
go
get that to
to
go to
the
the.
next speaker.
I can't get to go to the next chart. There you go.
Okay, thank you, our speaker.
Oh, here you go.
Okay, so just as a reminder, we only have one mic, so for speakers, as soon as you're done with the questions, please get mic'd up and we'll continue. So our next talk is by Howard Eller. He is the Chief System Engineer at Northrop Grumman Aerospace Systems. He's in the Space System Division. He brings over 30 years of experience in system and mission engineering to the development of space system concepts, spacecraft designs, and associated technologies. And over to you.
Okay. We took seriously the approach that we wanted, the redirect mission and the deflection mission, to use the same basic set of hardware. And I am briefing this for James Munger, so I'm a stand-in. So this is 3 separate briefings. One we did last time on the integrated sensing system. I have a single chart that kind of summarizes some of those conclusions. The middle one shows the configuration of the vehicle that we're talking about here, and this is the one that we briefed at the last one, which basically just adds the capture apertures, the astromesh-derived astrocapture we call them. This shows, our basic approach, a single suite of sensors that would give us long-range sensing. We get the ability to understand the makeup of the vehicle, and then as we come in closer, as we said at the last briefing, understand the rotational dynamics, and then a detailed understanding of the configuration. All of that focusing again on knowing where and how we're going to specifically engage the asteroid. Now, we took seriously all 3 of the approaches. The direct SEP approach is one that the asteroid redirect is featuring in spades. But we also, along with, just like Boeing, believe you could use, prior to that, you could do some type of a gravity tractoring, at least demo. It'd be difficult to get the measurements that you might want, but you could certainly show the topology and the layout. And then we've looked at the albedo modification. So there's, of course, 3 approaches. The no contact one is probably preferable in terms of simplifying your interaction. We did quite a bit of work looking at what it would take to sinter, which is more of this, to change the surface properties. And we believe that in the same volume of the two capture apertures that we showed, we could get up to a 50-meter, 250-meter apertures that would focus the sun and give us abilities, depending on how you focus it, to either sinter or ablade the surface. So that's a very interesting approach, and we believe it technically can be done. We've looked at it as a way of mitigating Earth orbit debris, and we think that works actually pretty well. Now, you're not going to ablade the whole asteroid, but you can change the albedo, and if you integrate over a 30-year period of time, if you know significantly ahead of time, then that change in albedo is a very significant change in delta V. Now, the question is, how permanent is your change, and can you control it? Can you project it? But this is one that we would recommend, highly looking at, because you could do both demos. The system that we showed before had two 20-meter capture envelopes, and on the back side of each of those two astromeshes, you could have a reflective surface with a variable focus for your, using the sun, and you can co-focus both of those. So you could both do the capture, and prior to that, you could do this, demonstration of changing a small segment of the surface to see what the change in the albedo is. So if you're going to touch it, the way that our team wanted to do it is to do some kind of an MLI, direct deposit. Now, the vehicle, I'm going to show that this is what our basic vehicle looks like, same vehicle. We had the two astro capture devices here for the redirect, but we can also install two arms easily along that volume, and this can also telescope if we don't want that much moment arm. So we can also put the sintering devices here. So this would be sort of like a tool rack where we would put those apertures and those appendages, the roll, the material, that we would then use to deploy and change a certain amount of the area of the asteroid so that we would get the requisite change in velocity. So this vehicle, for those who weren't at the last one, it's Eagle 3. This is the same system that JWST uses. There's a whole number of them in our system. It's a production line. So it has 1,000 kilograms of biprop, very strong CMGs if required. And this is the interface that we envision if for any direct contact that we would use. It can be custom tailored. It can be made to adjust depending on the surface properties, and it can be instrumented and have scientific and use some of JPL's actual capture apertures if required, in addition to the two arms on either side. The xenon tanks are probably the long lead in here. So we've worked with both ATK, PSI, and the Dawn tank, and both believe they could provide this in time to support the demonstration mission. So this shows two tanks that could both be built using their technologies. Both, the solar arrays are kind of a feature that distinguishes this, and this is the astromesh system. It stows in a cylinder, it deploys. Here are 7 of them at the time the paper was submitted. Now there's an 8th, and there's about to be a 9th put on orbit. This system, as I said then in the last briefing, is very, very stiff. In the RF application, because it's so lightweight, it's multiple tens of hertz in frequency, 100% on-orbit success. We suspend the solar array material here, and you have a whole set of different surfaces that you can add. You're not limited to just one. You could have solar array on one side and an RF on the other, or you can actually look through your RF surface. So if you want a high data rate pipe back to Earth, you can off-point the solar array and aim at Earth. and get both of those functions out of one aperture. So as we said before, this is being used on SMAP, and it's a very high rate of rotational rate stiff system. So when we look at what it does for 50 kilowatts, it has good blanket performance. The Astromesh itself for 12 meters is about 60 kilograms. You're looking at 3 times that for the solar array material. And we make the modules, solar array modules, into a structure that looks like this. And I had this in my panel, in my portfolio, so I thought I'd show it. So it stows flat, the solar array material stows flat inside the cylindrical structure, and then it deploys just like this. And so you can stow it and deploy it. And so that's that material. And it's formed in a rhombus to make that deployment very simple and straightforward. So in summary, we believe all 3 of these can be demonstrated on one mission. They could be added to the redirect mission depending on the mission timeline. And you could do a significant, this one's already being covered, so you could do albedo modification using the 20-meter apertures that were shown at the last briefing. CEP, of course, is enabling. That's the huge development here that would enable not only this mission, but a number of other ones. And we think power is a key one. One aspect of the power is you don't want to wrap your solar array around the asteroid. So that's why we think the 3-dimensional truss is a very good way to go for this. Any questions?
Thanks. Okay, we have time for questions. Any questions in the room? Any questions online?
Thank you very much.
Wait.
Oh.
Chairman's progress.
Chairman's progress.
Oh, okay.
Can you tell us if you did any analysis to look at how much of the surface that you would have to cover, and what's your operational concept for covering the surface with, say, an MLI, if you were to take that approach?
Let's see. We did have an analyst work that. So there's a spreadsheet solution. I think we could provide that. I don't have it here.
Okay.
We're envisioning this as more of a demonstration. You'd like to impact a significant fraction, so that then you could verify it over a number of years to show the change in velocity and direction. So I think we could give you that, respond with that. But I don't have it here.
Okay. And then also with the solar arrays, you got 50 kilowatts. That's both.
Yeah, 225.
225. Just wanted to confirm that.
Yeah, and it's not difficult to increase the diameter of that and to get significantly more, up to 100 kilowatts.
Okay.
The area goes up dramatically as you increase the area or diameter.
Okay. Got a question, Tim?
Okay. Yeah. Y'all haven't done an Astromesh solar array yet. Is that correct? In space.
That's true. We are in the process of doing the TRL 5 to 6 demo, building a module, and looking at testing.
Yeah, so my question was, what's the process for developing that? And you kind of answered that, so yeah.
Yeah, so there's going to be a phase 2. There's two participants in the phase 1 working with Glenn, and so we're looking at getting involved with that.
And do you have any idea when that would be space qualified? What's your time frame there?
Well, the requirement is to get to TRL 6 before the down select. And so we have an existing Astromesh, and so we're in the process of developing the internal solar array material. The other 2 participants are mainly doing a module for the TVA material, and so we're matching that on internal front. What would be hard?
There's a question about what the efficiency would be? The
The
solar array efficiency?
Well, we're using standard solar cells, and it's looking at operating at around 300 volts.
Right, but I mean like the mass efficiency. I mean, it looked like it was like 160 watts per kilogram or something.
Yeah, these are the efficiency metrics. So.
So 354 watts.
Yeah.
Okay.
So I had one question.
Sure.
No one else. Can you just, maybe you haven't thought about it too much, and if I missed it, I apologize, but can you go over a little bit about the deployment mechanism for the albedo change? Have you thought about how you do that with an asteroid?
Now, when you say, so there's two approaches. One of them is we would have either use these apertures, because once you're steady state, you only need one aperture, and that's your off point. So you could flip the other one and have a reflective surface on the backside that then focuses the sun, and you're basically turning the regolith to glass to get that's one approach.
So so it's actually a centering. So you're centering. Okay,
yes.
So you're actually changing. Okay, got it.
So that's one approach, and then the other approach would be to carry, and we haven't detailed out how you do. Anyone who's done wallpapering of a room knows, thin film management is a huge issue, and especially doing it autonomously, because you're not going to telerobotically operate it. So, what are schemes of having, discs or material and flying around, or basically, we're basically looking at using the arms, pulling the material, attaching it, and then cutting it and attaching it.
Yeah.
So, but we haven't put the brain power yet. We've only, drawn the box that we would fill in terms of detail. But we think that's a doable thing. And so the question, that's more attractive than paint, which will degrade with time and might not have the longevity. And then there's a question about whether there's a churning on the surface in terms of what happens, and so you might lose a surface coating.
All right.
And just to follow up on that, I know we're going to have some discussions from some of our presenters on basically solar ablation. When you're doing that centering, just a comment, you might want to look at not only changing the albedo and using that effect, which is a smaller long-term effect, but also the effect of doing that judiciously to provide a thrust, a blow-off thrust, and looking at the combined effect of those two things. So you kind of got a short-term and a long-term, but of course, if you capture the asteroid and bring it back, then you don't really have that long-term. So, but thanks very much. Good talk.
Thank you.
Okay, so our next speaker is Andy Turner, and Andy has been with Space Systems RAL for 30 years. He works in the advanced systems primarily on mission analysis and design. He's worked on mission operations of the Global Star Orbit constellation and on geosynchronous spacecraft, as well as the NASA LADEE spacecraft that was recently launched. So,
thank you, Dan. Good afternoon, everybody. Can you hear me okay? Everybody hear me all right? Hear me all right? Back? Good. Okay, glad to be here. I'm looking forward to talking about our affordable spacecraft, which is going to be simply a repurposed, redesigned geosynchronous spacecraft, just like one of the other speakers talked about. So we have a number of diverse asteroid deflection techniques we'd envisioned already, and one other thing I should say is robot arms are an integral part of our approach as well, because our company is owned by MBA, so we have access to that technology as well. So it's a nice synergy between the high heritage spacecraft and the high heritage arms, and it fits very nicely in with what Steve Stitch talked to us about yesterday about trying to collect all the high TRL items. I'll try to bear that in mind as I go forward. Okay, so a general sustained push, if that is indeed the approach that is the best, that would be set up by arms where we'd have perhaps a sort of hand at the end of the arm, as my colleague Paul Fulford talked about this morning. You could have a hand that simply spread the pressure over a wide area. Electrostatic tractor technique is interesting. Of course, we all know that Coulomb forces are much stronger than gravitational forces, so that's an interesting approach. We'd put one charge on the spacecraft, another charge on the opposite charge on the object, and then we'd use the Coulomb attraction between the two of them. We do a lot of work on spacecraft charging in our normal line of business because we have to be concerned with differential charging of our spacecraft, which use tens of kilowatts of power. So that's an approach there. My own personal favorite is the gravity tractor technique, which Dan, of course, must have worked on when you were on the KISS study at Keck. Must have been involved in that. I think that's an ingenious idea. And to me, it's appealing partly because it's the most independent of the nature of the asteroid. The asteroid could be a sandcastle, and you could still be able to move it gravitationally. Okay, because gravity, of course, gravity is a very egalitarian force. And lastly, we have the kinetic impactors. I didn't mean to skip over augmenting our spacecraft mass as a gravity multiplier, but that I'll be talking about a lot in my talk, so I don't want to talk about too much about it now. I'd also like to say that we can apply the techniques that were discussed by the two previous speakers. The ion cannon, we could actually do that if we wanted to, because we have envisioned using 8 thrusters. The way our spacecraft are configured with their electric thrusters, they all point in one direction for orbit raising, but we also can swing them 90 degrees so they can thrust east-west when we're in geosynchronous orbit. So we could have the east side thrusters perhaps direct thrust on the asteroid, and the west side thrusters provide the thrust to move the whole system. So we could adapt that, and with the robot arms, we would be in a good position to try wallpapering the asteroid if somebody wanted to have us bring along something that we could wallpaper it with to change its albedo. So 6 techniques really, okay, but I'll only discuss 4 here. So we have a flexible spacecraft system design that can handle any type. We could apply more than one of these techniques, as the previous speakers discussed. We could use ion cannon and the gravity tractor both. I think one thing that's very important, though, is we have to think about the person in the street, that they have to understand the importance of this project. And so we can report that we moved this asteroid out there in space, but the person in the street can't see it. I like the gravity tractor approach because it involves picking up mass, a large mass. I'm envisioning 160 tons, which is then brought back to Earth orbit. And of course, our astronauts, when they go up there on their Orion capsule, could bring back some kilograms of mass. I remember when I was a boy touching a piece of a moon rock in the Smithsonian. That was very exciting for me. I think a lot of the people in the street, who of course are the taxpayers who pay for all this, would like that. So our spacecraft configuration, this is a derivation of our 1300 bus. The previous speaker on his slide 6 showed one of our past spacecraft, which was NBSat, which was launched in 2004 and had a Harris deployed reflector, which we made good use of. That was the first spacecraft we ever flew that had electric propulsion. So for us, electric propulsion is already TRL-9, although we would change over to a higher thrust thruster, which is now at TRL-7. It's going through a life test right now. It's the SPT-140, which is made over in Russia. We have a rollout solar array, 50 kilowatts. We already have a solar array that's 30 kilowatts that's TRL-9 today. So this isn't a big jump. It's a much smaller jump in power than I've seen over the 30 years I've worked in my company. We didn't even do 2 kilowatts on some of the spacecraft when I first started. We could, of course, have a separable robotic servicing spacecraft. We've been working on development of that concept for DARPA for a number of years. I don't want to spend too much time on this. We have robotic arms, which I'll talk about in a minute, compatible with any launcher. So it could be SLS, Falcon Heavy, or Atlas V Heavy, perhaps. 40 kilowatts, that's an important number for electric propulsion. That corresponds to 2 newtons of thrust, which I'll be applying in a moment. And this is our versatile flight-proven bus. So that's, of course, TRL-9. We've launched 5 buses of this sort this year. The last one was within the last month. And that's a standard rate for us, about 5 launches a year of our spacecraft. We also work on a firm fixed price. This is important because it fits in with the affordability. We're very comfortable with firm fixed price for our products. Okay, we also on the side of the robot arm, this is the experience here, sort of a survey of the experience here with the various arm usage for the space station on Mars in 2 cases from MDA, our owner. And this arm right here is all ready for service. It's at TRL-9. This is TRL-9 stuff. It's actually flying. This is actually at the Goddard Space Flight Center today. It could be used on this mission. And we worked on Orbital Express, Phase A study. I worked on that myself for DARPA 10 years ago. And the DARPA Phoenix, we're working on that today, which involves retrieving antennas from spacecraft that are in orbit today and reusing them in GEO. So this is a propellant budget. This comes out of my own career. For many years, I worked on this before I changed over to Advanced Systems. I was with our Mission Analysis Department. One of my jobs was doing these propellant budgets. This is the most fun propellant budget I've ever done because it's the propellant budget where we're actually adding the mass of an asteroid to our spacecraft. So we start with the 14,500 kilos at launch, which is a common thing with one of the previous speakers. That's on a full-size launch vehicle. We go through we get into an orbit where we loop around the moon, which gives us the boost to get into deep space. And then we have electric propulsion augmenting that delta V to get to the asteroid. So as you see, the spacecraft mass comes down a little bit more than a ton to reach the asteroid. Now suddenly the spacecraft mass is increasing by 160 tons. That's when we pick up the boulder from its surface. We have to land on the big asteroid. We're going to pick up a rock, as the alternative approach from NASA Langley discusses. Pick up a rock. We're going to need to use our biprop system to haul the rock away from the asteroid because the attractive force between a 200-meter asteroid, which is the size we targeted, yesterday, when I was talking to Lindley Johnson after his presentation, he said there were probably about a dozen or so, 14 or so objects of this size in the range that's easy to reach from Earth and easy to return to Earth. We'd be going to one of those. We'd pick up the rock. We're going to need we need 7 newtons of force to pull this rock away, this boulder away from the 200-meter object. And we're going to use our bipropellant thrusters. That's our heritage, too. We've been using those for many years, 22-newton thrusters. I heard somebody mention that earlier today. We have 4 of them operating together, 80 newtons of thrust. No trouble lifting it away. So then we're going to pull off to a distance of about 90 meters. And at that distance, we are ready to acquire the asteroid. At that distance, what we do is turn on the electric thrusters, which generate an astoundingly large 2 newtons of thrust. Taking about 40 kilowatts of power to do it. That exactly balances the gravity force that's trying to pull our augmented spacecraft mass down to the 200-meter large asteroid. So we've got balanced forces here. We're not approaching it. It's not approaching us. But there's thrust on the entire system. So the asteroid is accelerated. For this demonstration, we said we'd do 0.001 meters per second, delta V, which I recall was in the Keck study as a demonstration number. With Doppler measurements, we should be able to see a velocity change that big. It takes about 2 months to do the maneuver. Notice how here the spacecraft mass, I'm treating it as 6 million tons. This is the heaviest spacecraft in history. So then, of course, we have to, this is the gravity tractor operation. You notice I have an efficiency factor of 0.7 there. That's because I'm steering the thrust away from the asteroid. Okay, so I'm getting a cosine loss there. I actually don't want to let the ion thrust touch the spacecraft, the asteroid at this time, because I don't want to charge it up. Okay, I don't want any repulsive charge that's larger than repulsive electrostatic charge is bigger than the attractive gravitational force. I'm going to use the biprop thrusters to pull away from the big asteroid. And then I use the electric thrusters to bring this 160-ton boulder that we acquired home. So we only use about 7% of the total impulse on this mission on the gravity tractor. Okay. So just a little cleanup discussion here. These are the numbers I was telling you about, 2 newtons of attractive force between them when we're doing the gravitational tractor. That corresponds to a distance for a 200-meter asteroid of about 90 meters. So we're actually about half a diameter away, about 1 radius. That's sort of shown graphically here. We're physically actually relatively close, although this distance is still 90 meters, so we can still turn the electric propulsion thrust away so it misses the asteroid. This also helps us stay out of the asteroid shadow, because if we go into the asteroid shadow, we're not going to get any power to run our thrusters. Very important. So I have a couple last few points here. What if we can't extract the boulder? Well, then we're going to push on it instead of gravity tractor. What if it's a rubble pile, but it only contains sand? Maybe it's a sandcastle. We use the arms to scoop. Just scoop 6 tons, put it in a bag. What if 90 meters is too close? Then we can bias our thruster thrust down below 2 newtons. We move off to a greater distance and have a smaller acceleration, take more than 2 minutes. Okay, so a little bit of background here. We have Itakawa, rubble pile, different scales of rubble. I think what we'll really find, not a hunk of sand, but just a bunch of different pieces of rubble, and we'll just pick up the boulder that's the right size from the bunch. If there's a slight rotation on the asteroid, maybe we pick it up from the north or south pole of the asteroid to minimize that. That's why on my propellant budget I didn't have a D-spin term. It's one of the beautiful things about picking up the boulder from a big rock, a big asteroid that's a rubble pile. It's probably going to have less than the 2 RPM spin. So the D-spin is probably traded away as a problem. We do pick up the problem of having to lift it off its surface with more thrust than the electric thruster can provide. So also look at this large population of rubble pile asteroids. Probably what we have. Okay. Thank you.
Thank you, Andy. All right, we've got time for a couple questions. Anybody in the room like to? Here we go.
So 100-meter asteroid.
200 meter.
200-meter asteroid. Very nice talk, by the way. 200-meter asteroid might be rotating at, every 10 minutes if you're unlucky.
Mm-hmm.
And of course, you probably can pick the one you do for a demonstration, but if you actually had to do this, you don't get that option. You have to go to the one that, is the one you want to move. Where does rotation sort of break this down? What's your maximum rotation rate you could
Well, like
tolerate?
I said, if there were a large rotation, I would go to the north or south pole to pick the boulder up. I think what will happen in real life is that we get near the asteroid and we start examining boulders. What will happen is all the scientists will be competing among themselves to have us pick up the most interesting boulder. And I think one of the trades will be, what's the latitude of where that boulder is on the rotating asteroid?
Yeah,
I think a high latitude one.
It might make it easier to get off if it was like lodged in. Once you unlodged it, it would tend to, go away.
I'm counting on the high thrust from the 80 newtons of thrust, which is more than enough to muscle away a very big boulder from the asteroid to get us loose. I don't think we need to pick it up from the equator to get a higher velocity. Any other questions?
Any questions online? Okay, and again, I'll encourage folks that are online to submit your questions. #ProtectPlanet. Okay. All right, well, thank you.
Okay,
Thanks very
thank
much.
Okay, our next speaker is Dr. Bonvie. He is the Vance Kaufman Endowed Chair Professor of Aerospace Engineering and the founding director of the Asteroid Deflection Research Center at Iowa State University. His current research focuses on the development of space technologies for mitigating the impact threat of hazardous asteroids. Dr. V.
Okay, thank you. Actually, my talk is not about flight demonstration proposal, so I'm going to have an overview of many different options for NASA consideration, also your consideration. So I'm not going to promote any particular concept. So during the next 15 minutes, so this may not be a good place to talk about nuclear options, so I will minimize to talk about nuclear options. So I'm going to just spend about less than 1 minute to have an overview of planetary defense 101. If I don't go through this one, there's always confusion about deflection, disruption, warning time, so many issues. So let's have a very brief review of sort of basic concept behind planetary defense. And what I'm going to state today is all from 2006 NEO report by NASA, as well as 2010 NEO report by NRC. So basically, when we have sufficient warning time, yes, deflections is the best choice. But if we don't have a sufficient warning time, then deflection is not option. So we do need something other than gentle deflections. Then we may have to accept disruptions or fragmentations, but that is also quite misleading. Once we talk about disruption or fragmentation, we are expecting that orbital debris will become much, much larger, at least within about 15 days after the impact. So let's agree that we do need early detections to be able to utilize gravity tractor as well as kinetic impactor. But if we don't have a sufficient warning time, we have to accept that other options, which is not 100% perfect solutions. But if we have less than 1% of impacting mass compared to original mass, that may not be a bad option. So the second chart on planetary defense, as I mentioned, warning time is the most important issue or concern from engineering side. So I know there's many faculty researcher from JPL. That's your task to give us plenty of warning time. So target size, very important. Mission cost is also very important. We cannot just afford very heavy vehicles, which I heard this afternoon. And also uncertainty, political concern, disruption versus deflection. Those two should not be fighting each other. They are complementing solutions. But I have two red dots, as you remember, 2012 DA14, and as well as the small, but it's a large, it's a very oxymoron kind. It's a small but large. The Chelyabinsk media with almost zero warning. So I have two dots we have to worry about. DA14 has 1 year lead time. Am I right? 1 year. But we had near miss. We were very lucky. So let's even think about case. Civil defense evacuation is good solution too. So we have many different options to be used for many different situations. So I'm going to present three topics. Topic one is ARB-based kinetic impactors, as well as multiple gravity tractors. Second topic is about the use of a nuclear device. And third one is very special case. What if we have only 1 hour warning? Are we just going to wait? But we should think about that. So I'm here to present this sort of notional idea to utilize 40 kilowatt asteroid redirect vehicle with capture 7 meter asteroid. 7 meter doesn't mean exactly 7 meter. It can be 5 meter, 7, 10 meter range, and mass will be about 500 ton. It can be 500 ton or even 1,000 ton kinetic impactor, depending on the mass. So when I was preparing proposal to NASA, I think that this was the only thing I was able to come out, how to utilize 40 kilowatt, good-looking, heavy vehicle. So this is the one. So idea is not mine. It has been well known. So basically, once we detect the large asteroid, then we find a small asteroid and guide that 500-ton kinetic impactor to have proper kinetic impact. Sounds very fictional, but this is one option to utilize 40 kilowatt ARB as a kinetic impactor. However, total energy contained in this 500-ton kinetic impactor can be replaced by, say, 10 kiloton nuclear device, which will weigh, say, 10 kilogram or even less than 100 kilogram. So we have to think about cost comparisons. Yeah. How much is it to launch 100 kilogram payload, which can be easily launched by using small launch vehicle. So these are the proposed research topics if NASA likes to have this kind of application. This is not a complete solution. We have to go through optimal search, selection, of small asteroids. We don't have a database for 5 meter or 10 meter size. We don't know. We don't know where they are. So assuming that during the next 10, 20 years, we have 1 million small asteroids, we have a database. So once we know the 100-meter asteroid is appearing somewhere, then we run our supercomputer to find the best trajectory to pick up the smallest one, and then hopefully those two are flying along the same direction. Then that's the optimal solution. We may find out that kind of optimal solution. Also, someone may propose that, or we cannot do that. We have to pre-place many small asteroids around the Earth. That's the Russian concept. And another concept is to utilize Earth's gravity, Jupiter, the Mars gravity, a system maneuver to get more delta V. So there are many academic research problems which needs to be done. And please do not expect that someone should have done all this research so that I can present those. No, it requires funding. Somehow that doesn't look good. Then we have another option to utilize solar electric propulsion-based gravity tractor, as we heard this afternoon many times. But I didn't realize that we currently do have such a high, heavy satellite with such powerful 50 kilowatt energy source. So whenever NASA studied gravity tractor in 2008, NASA thought it's just like a 1-ton class, maybe 2-ton class gravity tractor. So at that time, I don't think we couldn't dream about 20-ton class gravity tractor. It's a brand new story to me. So at that time, we have, here is simple gravity tractor. And then I have a few, I'm gonna use, here is. This is a gravity tractor, basically or shooting this. But if there's a debris issue, then we have to tilt. So that's why the traditional gravity tractor will require 2 tilted jets. So continuously firing. That's a basic concept. So this is one equation we do need gravity tractor design. The gravitational pulling force is determined by available thrust. I heard about augmenting boulder. I have to figure that out, how you get better performance. But basically, given design, gravitational pulling force is predetermined by the maximum available thrust. Whether you add more gravity, the boulder or not, still that will need to be adjusted, that separation distance. So I will be paying more attention to your new gravity tractor design. So at that time in 2008, so this is so-called single point failure. What if there's a malfunction of the single platform? So we created halo orbit. The satellite will be orbiting around like this, using only one engine. And in one orbit, we can place a couple of, depending on the orbital radius. So it has redundancy, improvements, reliability issue, but still it requires more engineering study. So multiple solar electric propulsions based gravity tractor. We don't need the ARV. We don't need a bag or something like that. We just solar electric propulsion based gravity tractor in halo orbit with multiple formation keeping phase. We will have much better efficiency. Few minutes before I talk to next topic of nuclear, we have to understand that once we have heavy gravity tractor, instead of operating 2 years, as I heard from Boeing or Northrop, or maybe 10 years, the best solution is to use gravity tractor as a kinetic impactor. We don't have to wait 10, 20 years to operate, even 2 years. The total delta V resulting from the use of gravity tractor as a kinetic impactor is at least 10 times better. But someone may say that, we cannot guide in the right direction. There's many, many different open issues. But anyway, there is a sort of option to be considered, but yes. So I complete my original presentation of those proposed concepts of utilizing ARV as a kinetic impactor or gravity tractor or multiple gravity tractor. So next couple of minutes, let's talk about short warning time. So once we have a sufficient warning time, no problem. Somehow we can solve the issue. But what if we don't have a sufficient warning time? Deflection is not an option. Then disruptions, fragmentation, and dispersion is the only option other than simply waiting or civil defense. Let's look at the 2012 DA14. So this is more like a promotional talk. So I have NASA NIAC Phase 1-2 study being funded by NASA. And the title is an innovative solution to NASA's new impact threat mitigation grand challenge. Nowadays we hear about grand challenge, but it's nothing new. The grand challenge by NASA on neo deflection has been around more than 3 or 4 years. And Brent Bobby is my co-I, and the task is to develop practically viable, low cost, technically feasible, blended kinetic impact and penetrate subsurface nuclear explosion concept, technique, method for mitigating neo impact threat with short warning time when deflection is not an option. And this is basically illustrations, fragmentations. If we have at least 15 days, we will have this kind of orbital dispersions. Then the Earth will go through that, so less than probably 1% mass will be intercepted by this cross-section due to gravitational pull of this. So that is a result, but it's an illustration. Not that many, but not that big. So this is a base concept being studied by our group. And also, I just want to emphasize that many of you think that even though you are against the use of nuclear device, many of you think that last option, yes, let's use that. But that is not that simple. For the last minute option, the arrival velocity will be much larger than 10 kilometers or even 20 kilometers per second. So we cannot afford rendezvous. So we cannot utilize a nuclear device. Let's assume that here's a nuclear warhead. Just hit, penetrate. No, that doesn't work. And contact surface, stand up, is much, much less effective. We are wasting all the energy. So the best solution is penetrate, have a subsurface explosion, but that is only possible when the speed is less than 300 meters per second. So only option is before last intercept or impact, we have to release the payload, and then the satellite will make kinetic impact, make a crater, and then the payload, nuclear payload, will have explosion under the crater with about 1 or 2 millisecond delayed explosions. I think I will just stop here. Yeah.
Okay.
Thank you.
Right. Thank you. We have time for one very quick comment or question, please.
So a real quick question. In military terms, if you have one large nuclear weapon, it isn't as good as having a lot of small ones. So you increase the kill potential by MIRVing.
Yeah.
So I'm assuming that you think you're going to get enough material off the face of the Earth, so even though you have many, many hits, it's less of an impact. Is that true?
What do you mean, the debris impact?
Yeah, so if you...
Oh, yes. Our computational simulation showed that if we have at least 2-week lead time, 300 meters, using 3 kiloton device, which can be easily launched by Delta to small launch vehicle, net mass is less than 0.1%. The debris size already much, much larger.
Okay, so most of it misses the Earth, period.
Yes.
Okay.
And then hopefully our atmosphere will protect us.
I see.
Yes.
Okay, thank you.
Thank you.
Okay, thank you. I think we have to move on.
Okay, our next presenter is Dr. Jeff Landis, is a scientist and he's also a science fiction writer. He has a degree in physics and electrical engineering and currently works on developing advanced technology for space missions at NASA John Glenn Research Center. Dr. Landis is joining us virtually, so are you there? Okay. Hey, Jeff, Are you there? Can you hear us?
Yeah, hello, do you hear me?
Yes, we can.
I'm not sure. Can you hear me now?
It's a little bit faint. If you could try getting maybe a little closer to the microphone, we'll adjust the volume here if we can.
I am good. Can you hear me?
Can you hear me?
Hello? Okay, I don't seem
Yes. Are you there? Can you hear us?
actually, hello, do you hear me?
Yes, we can.
I'm not sure. Can you hear me now?
It's a little bit faint. If you could try getting maybe a little closer to the microphone, we'll adjust the volume. Hey, Jeff, can you close the Ustream link there so that we're not getting a feedback? There's a significant
I seem
delay.
to be coming through with quite a bit of delay. I think that may have been that I was switching between my computer and my phone. But on the assumption that you can hear me, even though I cannot hear you, I should keep going. Can you confirm that in the chat window that you can hear me? Okay. Okay, well, great. Okay, I'm Jeff Landis. We're doing an analysis of whether we can use asteroid repositioning for planetary defense. And I do need to acknowledge the COMPASS team. In fact, I need to acknowledge two studies. First, the study we did for the Keck Institute for Space Studies on asteroid repositioning, and then we used that for a white paper submitted to the NIAC solicitation last spring. The problem, which has been already quite a bit discussed, so I perhaps don't need to go into great detail on this, is that asteroid impacts are responsible for mass extinction events, including the very well-known Chicxulub event. And the probability of this happening in any generation is low, but the consequences are very high. So we'd like to find a means to divert an asteroid. And several such means have been discussed in the previous talk. In previous work, we've done a study on behalf of KISS, the Keck Institute for Space Studies, of how to design a spacecraft capable of moving a small asteroid. And in that study, we looked at a small asteroid, a 7-meter class near-Earth object with a mass of perhaps as much as 500,000 kilograms. So it showed that we could do this. Here's just one of many visualizations. There's been any number of such visualizations that have been done since we did that study about 2 years ago now. But it looks like we can pick up an asteroid and move it into a near-Earth orbit, in fact, into a halo orbit, either low around the moon or around a Lagrange point. Well, directly relocating an asteroid by SEP just takes too long to be a way to defend the Earth unless you have an enormous amount of time. But we still think we can use this asteroid relocation technology as a method of protecting Earth. In fact, this was alluded to in the previous talk. We proposed taking one of these 7 to 10 meter diameter asteroids, finding it, bringing it to a position in halo orbit, perhaps in one of the stable Earth-Moon Lagrange points. From this point, you can eject the asteroid with comparative low delta V into an escape trajectory. So the proposal then is to use such an asteroid at the Lagrange point as a defender. And here's just a graphic showing it. You can take your small asteroid is captured, brought with solar electric propulsion into a translunar halo orbit where it's kept, and that will be your defending asteroid. When you have warning of a larger Earth-crossing object approaching, you can then send your defending asteroid out in order to be a collision. As the previous talk mentioned, the hypervelocity impact is a very efficient way of moving an asteroid with delta V. So the object essentially is to hit an incoming bullet with a bullet of your own. So when the threatening asteroid is detected, the path is calculated, and we eject the defense asteroid into a trajectory to intercept it. We can do mid-course correction as we learn more about the final trajectory of the impact. The resulting impact will be typically at velocities on the scale of about 20 kilometers per second, which transfers momentum to the impacting object. So just showing that this can be done. We know this can be done because it has been done. Here's just a view of the Deep Impact Probe, which successfully impacted Comet Tempel 1 at a high velocity. So that shows that the navigation needed to do this is a known thing, something that we can do. So a lot of calculations are needed. How large a threat can be addressed? How much delta V do you need? How much can you achieve? How big does the defending object have to be? The bigger it is, the more impulse you get, but it obviously takes much longer to move into place. So that brings to the question of how much advanced warning do we need? The longer the warning, the lower the delta V. And final question is, does the impact threaten to fragment the incoming object? And if so, does it make the problem worse or does it make it better? Well, there's two different ways that we can think about intercepting an incoming object. So the incoming object in this picture would be in the red trajectory. It's in an orbit. Obviously, the orbit will cross Earth's orbit every orbit, but only one particular time of crossing is the Earth going to be in position that it will be threatened. So in strategy 1, you intercept the orbit when it passes, you intercept the asteroid's orbit when it passes Earth's orbit at a first time, even though it's going to actually impact the Earth on a future path. So this is a method that allows you to do the interception with a little bit more advanced warning. So the impact will change the phasing of the orbit so that it returns when the Earth isn't there. So by intercepting well in advance, a relatively minimal delta V is needed. It's worth noting you can intercept it at either place. It could be either in an inbound path or in an outbound path. However, if the asteroid is at high inclination, if it's at high eccentricity, it may be difficult to reach on the outbound path, assuming that the impacting path is an inbound path. The alternative is, well, what if you don't have that luxury? What if the asteroid is approaching Earth and you don't have the ability to perturb it on a previous path? You have to perturb it now. In this case, you have a lower amount of time. You have a lower amount of distance over which you can affect it. So you need to move the defending asteroid further away from Earth in order to give the impacting delta V a chance to perturb the asteroid's motion enough to avoid the impact. So that's a shorter warning. It will require higher delta V, so only relatively smaller asteroids can be deflected if you don't have the long amount of warning. So how much impulse is produced by interception? There's actually two things that you get. You get momentum of the intercepting asteroid. The asteroid coming in gives the delta V comparable in general to the target's flyby velocity, give or take. However, it also produces a reaction force. The impact produces a large amount of ejecta. Basically, there's a fireball produced by the impact that ejects a plume of vaporized material. The vaporized material will shoot out and produce additional delta V. For a very simplified calculation, this will depend on a number of different parameters, including how deep the impact is. But for a simplified case, you can calculate the reaction impulse produced as roughly on the order of half the incident momentum. But it can be much larger or much smaller depending on the details of the collision. So if we ignore that reaction impulse, it's easy enough to see that the delta V achieved is just the ratio of the masses times the relative velocity. So putting that into an example, if the interceptor is a 1,000-ton, 8-meter category asteroid, we're looking at a target that'll be a 500-meter, 200 million ton asteroid. We'd get a delta V of about 5 centimeters a second at a relatively conservative impact velocity of 10 kilometers a second. So that will shift a asteroid position by on the order of 5,000 kilometers per year. And that's accounting for the magnitude but not the direction of the momentum. With that, it would take about 2 years of advanced warning to shift the orbit, to shift the phasing by about 1 Earth diameter. So that's a quick back-of-the-envelope calculation of what kind of advanced warning you need. So the calculations there basically suggest that the technique of using an asteroid to intercept an incoming asteroid should be feasible. It's something that will need a warning time typically of greater than a year. It's not something that with these small asteroids will give you a fast response, but it is in fact a reasonable thing to do. The rest of the charts are mostly just backup charts, but basically this would be the class of asteroid that you could deflect with about 2 years of warning would be a continental class of impactor, not a global, but on the other hand, the very, very large ones are extremely infrequent. So you could deflect one of the more frequent but still catastrophic impactors. And that, I think, is it for the presentation. I guess, are there any questions?
Okay, thank you, Jeff. Can you hear me? Can you hear us? Can you type and we're still not coming through? Is there... Okay. Are there any questions? We can kind of queue it up here if someone wants to ask him a question.
Yes, I can hear you, but only by the technique of turning off my phone and turning on my computer and vice versa.
Okay.
So, and there does seem to be a bit of a time lag here.
Okay. We don't have any questions here in the room. Pedro, are there any questions online? Okay. All right. You might get this message in a few seconds, Jeff, but thank you very much for your presentation. You can see us either. Okay.
All right, we'll move on. The next talk is by Tim McCraff. Has worked at the Jet Propulsion Laboratory.
Okay, thank you.
Since 1984, recently he has done mission design on several proposed missions, including Moonrise, ISIS, which is discussed later in the session, and the Asteroid Redirect robotic mission. Thanks.
Okay, thank you. Let's see, am I controlling this? Okay, so then the question is, how am I controlling this? Okay, that works. That work? Okay. Okay, so at the time I wrote this, I couldn't think of any other way that didn't involve physical contact, but of course, you know, I'm being educated. Anyway, let's just say that it's a nice method of not having to touch the asteroid very much to move it. So, as we've heard before, you know, the gravity tractoring the spacecraft weight equals, that's the connection between the spacecraft and the asteroid, and so that limits how much you can pull on it. You know, as we've seen in various ARV designs, it's easy to get 1 to 2 newtons per spacecraft in the 2 to 4 ton range. But unfortunately, the spacecraft weight for asteroids under a kilometer in diameter is well under a newton, and so most of the spacecraft thrust capability is not used. So it's very propellant efficient, but very time inefficient. Now the weight formula, if you assume a spherical asteroid and you operate at an altitude of 1 radius, which is about the closest you could imagine operating with any degree of safety at all, is this equation here. And the only free variable once you've picked the asteroid, or if the asteroid's been picked for you, is the spacecraft mass here. So that's the only way to improve the coupling. Now you can't take a bigger mass with you beyond, maybe you could imagine a 20-ton spacecraft, but at some point you can't launch it, and if you do, it takes much longer to get there, and time is not your friend. So, so clearly, you need to add mass once you get there. Let's see, that one works. Okay, so I'm not a mechanical systems guy. This is Brian's problem. He'll figure it out if we do this, but or somebody like him. But I did want to mainly I want to talk about what you could do with an augmented mass, but I did want to point out that there are at least a couple of things I could think of, and there's probably a bunch of others. Of course, you can grab a boulder, like as is being studied. There's also the brush wheel sampler that we've used for sample return mission concepts, but in principle, if you make it bigger, it just grabs more mass and flings it up into the collection area. And that doesn't take a huge amount of time to, I mean, it might be days, but it's not weeks or something. So in either case, I'm going to assume that we can get 1,000 tons into this box here. So, gravity tractoring operations, as we've talked about so far, the center of mass of the spacecraft wants to be as close to the asteroid as possible, but of course, because of the thrusters want to be far enough away that they don't have to cant very far to avoid whacking exhaust into the asteroid. So these are kind of competing desires. If you have collected mass, then it's relatively easy to leave that mass on the down close to the asteroid, as it's kind of shown in this cartoon. Now, for gravity tractoring, typically you want to adjust the orbit in the downtrack direction, because this generates a secular, you change the period, you get a secular downtrack trend. And so, here's another little cartoon that says, we thrusted and gravity tractored for a while, and then we got this sort of linear trend that runs off for infinity. And of course, I'm not showing the once per rev signature. So what can we do with this sort of approach on a real asteroid? Well, 2000 SG344 is kind of a fun asteroid. It's in a very Earth-like orbit. Dan and company did a study that said you could get 3,000 to 7,000 tons back from it in 2028, but unfortunately the asteroid is several times larger than that. On the range you see, 10,000 to 300,000 tons. So clearly the whole asteroid's not returnable in a ARV, grabbing it sort of approach. So let's make some mid-range assumptions. 50,000 tons of asteroid mass, 1,000 ton spacecraft mass after we've augmented it at the asteroid. And if you do the math, you come out with almost 2 millimeters per second per day, with cant angle losses and so forth. And so a meter per second only costs 2.4 tons of xenon, so clearly several meters per second, not 10, but several, can be accomplished with the sort of spacecraft that we're contemplating here. Now, an interesting thing is that if you start doing this in 2021 and you do 1.25 meters per second, which takes just under 2 years. Well, let me back up a second. So the red is the trajectory unmodified of SG344. It does, it comes by the Earth kind of 3 times, 4 times, however you want to count it. If you make this modification of it, in 2021, or a slightly larger modification if you start later, it's only off by 650,000 kilometers here on this first little green arc that you can see. But it turns out that that's enough to capture it into this sort of orbit for 35 years, and then eventually it wanders off the other side. Now, that's just when I stopped looking. I could probably make it last here for even longer if I tried. But 35 years is, longer than any of us probably care about. So it's kind of interesting that you could, for a relatively modest effort, you know, stick this 50,000 ton mass out there in essentially near Earth space. So another interesting example is Apophis, which of course has the keyholes and all this business. Well, you know, the 2029 we're not that worried about at the moment, right, Paul? Are you worried about that? Yes. Okay. So, and it's 10 times bigger than SG344. So, using a slightly different set of assumptions, because this is actually getting to be big enough that you don't have to pull up all that much mass. You know, with the same sort of thrust level on the spacecraft, you get 3 microns per second per day, which, you know, doesn't sound like much, but if you do downtrack thrusting for 1 revolution of Apophis, you get, you know, 90 kilometers per rev. You do this for 3 times, it's 270 per rev. You go 10 years, as you see, it's starting to make a big difference. And so, I guess my point here is that, you know, this is starting to be of order the diameter of the Earth. It's not, you know, I mean, obviously the Earth's twice that big, but, you know, you might find that there's cases where a couple thousand kilometers is enough to get you out of trouble. It's certainly enough to move it around on the surface, and maybe you could stick it, you know, I don't know. Don't really want to go there, I guess. But the point is that if you know, typically gravity tractoring is thought of as, this is just good for a minor trim. But if you can augment the mass and you have, you know, some time, you can actually use this as the primary method for moving the asteroid, with, you know, the Earth's radius as an important parameter. So, you know, in conclusion, you know, mass augmentation makes gravity tractoring an attractive primary method for moving asteroids. It uses all the spacecraft thrust capacity. It works on asteroids as big as Apophis, and probably even a little bit bigger, although really long lead times would be necessary. And of course, you don't have to despin the asteroid. In fact, if you're doing this brush wheel sampling thing, you probably don't want to despin the asteroid, because you want the asteroid to rotate stuff under your brush wheel sampler so that you can just keep, you know, grabbing it up. But, you know, other methods are probably possible. You know, and again, how you would actually augment the mass is an interesting question, and I don't know that neither one of these feels like the absolute perfect way to do it. But you know, something is probably out there. And then, you know, like as I showed, SG344 is kind of a special case that could be an interesting, if it was moved in this manner, it could make a long-term interesting target for human missions and, you know, ISRU utilization, whatever. So that's all I had.
Great. Thank you, Tim. Okay, do we have any questions, comments in the room? Okay.
So, I'm curious about the, you know, if say that the asteroid deflection mission wasn't flown, could this be combined somehow with the ARM mission? I mean, because it seems like the crucial thing is, you know, that you'd want to sort of bring up the TRL level on is, how do you actually get the mass from the spacecraft, from the asteroid?
Right.
You know, if we've done it for the moon, you know, we can speculate for asteroids. We don't really know, and so it'd be nice to have a test. And so, could this be like? It seems like this potentially would be a vote. If you couldn't do both missions, having if you heard this morning's session, you know, you pluck something from a bigger body, could be combined with this. It seems like very, very nicely. In other words, you could actually say, yeah, we can get stuff from an asteroid because we plucked it from some bigger body, you know, and brought it back for scientific tests, but we actually did it. And so I was just sort of wondering what you think about that.
Well, yeah, I mean, it's not obvious. I don't think there's any way to combine this with bagging the whole asteroid on the same mission.
Yes, I would agree.
But, you know, obviously if you're bringing back a small part of it, if the small part of it is still big enough to do gravity tractoring, then you can do gravity tractoring after you grab the smaller part of the asteroid. So, on the other hand, I guess I would say that well, okay, gravity always works, right? And arguably, this is not something that really needs a ton of demonstration, but if people are worried about it, the reference ARV is perfectly capable of gravity tractoring these little asteroids and detecting the results and making, and having a mini sigma detection of the results. So I mean, we can demonstrate gravity tractoring with either mission. We just can't demonstrate gravity tractoring where we moved a large object a long way with the reference mission. It would have to be the grab a boulder or something equivalent to that.
So, but yeah, that wasn't quite what I was saying. I think that there's no physical doubt that the gravity tractoring will work. There seems to be no physical reason why it wouldn't work. It's very simple, straightforward. Newton would have thought of it. Yeah. But grabbing the material from using a chain bucket or whatever it was you're talking about to grab the material from the surface, that seems less, I mean, obviously you could make it work, but it seems like a less secure thing at the current level of TRL.
Sure,
and
but
that
that's
would be worthwhile testing if you could.
Sure, no, that's true. And I mean, the grab a boulder approach, in principle, would be a major step in that direction. And if that works as expected, I don't know why you would mess with the brush wheel sampler, except that you could maybe get more mass that way because you're not depending on finding a right-sized boulder. So that's kind of the trade, But yeah, like I say, whichever way you're going to grab stuff, clearly you would want to. You probably would have to sneak up on grabbing stuff if you were seriously going to move this, and not make it the first mission, unless it was just a demo in the first place.
Do we have any other comments or questions?
Okay, we're a couple minutes ahead here, kind of outside my threshold here. I was keeping it to the 2-minute delta here, so we got about a minute. I'll just echo that, a lot of these presentations dealt with a similar concept, but what I hoped, or what Pat and I hoped when we put this session together and we chose the R5 responses, was that there would be nuggets from each of those, and I'm clearly seeing some thoughts and some ideas that have come out that we'll talk about more in the discussion, kind of a little unique twist to each of the presenters' approach that may have some more interest in being looked at. So that was a comment to kill 30 minutes there. Okay,
just a general question. I've heard that the inner solar system is non-deterministic, the Jupiter and beyond are deterministic, and that we have a very poor gravity model for the internal solar system. So, all of this analysis would seem to be, dependent on us knowing exactly what a certain deflection is going to do, because, we all could be making things worse. Yeah. So somewhere in maybe the final comments, it could be, a better model of the inner solar system would be a corollary to the design of this mission.
Okay, let's hold that thought. I think, for example, Paul Chodas can vouch for the fact that we do know the solar system pretty well, and we can predict with gravitational effects. If there's non-grav, that's another issue, but for quiescent asteroids, we can predict with sufficient knowledge very far into the future. So we can talk about that more in the open discussion, but to get us back on topic here with the presentations, our next presenter is Josh Hopkins. Josh is a space exploration architect at Lockheed Martin. He was the editor of the AIAA's International Reference Guide to Space Launch Systems, and a technical advisor for the science fiction movie The Europa Report, which I haven't seen yet and I'd like to see, so I'd like to talk to you about how do I get a copy. Anyway, Josh, go ahead.
Thank you. So I'm filling in for Darren Wade, who came when we first held this conference but wasn't able to come this time. So any questions that I can't answer, I'll defer to him. So we've been talking about asteroid deflection for a couple of hours now, and I was struggling to think what I could say that hasn't already been said. I'm going to try to focus on some specific aspects that we've been looking at, but some of this will start to appear familiar now that we've had a couple of talks on gravity tractors. So we approached this sort of from first principles and thought about two things. One is the question was kind of how do you make ARM useful as a planetary defense demonstration? And the issue is that the small asteroids ARM is currently scheduled to visit really aren't particularly dangerous. You want to prove that you can deflect a dangerously sized asteroid And the techniques, at least the way that ARM is currently conceived, probably don't scale very well. So you're probably not going to de-spin a really large asteroid. The size that would be more useful is something in the 100-meter range, give or take, say, a factor of 3 in size, which equates to roughly a factor of 10 in volume or mass. So below something like 30 meters, those asteroids are common but not very dangerous. Above about 300 meters, they're dangerous but not very common, and most of the ones, say 2/3 of the ones above 300 meters or so, have been discovered. So this somewhere in the high tens to low hundreds of meters diameter is the size range we're interested in. That corresponds to something on the order of 1 million tons of asteroids move. And the deflection we decided we want to achieve is on the order of 1 centimeter per second. That came from the study of how to deflect asteroid 2011 AG5 when it was one of the top items on the risk list a couple of years ago. That's also a big enough number that you can measure it so that you can confirm that you have actually deflected the asteroid. Now there's, I think, another important point about what the question was, which is that it's not really a question of what's the best asteroid deflection demonstration you could do. It's what can you do with the ARM mission. So what we really need to do is figure out how we use the spacecraft roughly as conceived by ARM with the ARM mission objectives and add on a deflection demonstration. So things like deflecting kinetic impactors, well, those might be a really good way to deflect an asteroid. It's probably not something we can do very well as part of the ARM mission. Likewise, there are a number of techniques that have been talked about for potential deflection that could be done sort of as secondary payloads or additional capabilities on the ARM spacecraft, but we are very budget constrained on this mission. There is literally no budget in the current NASA allocation. So anything that adds additional systems specifically for asteroid deflection on top of the ARM requirements is potentially a deal breaker. So we wanted to figure out how to do a useful demonstration basically with the ARM spacecraft with as few modifications as possible. And we got very interested in a comment that Dan had made in a hallway conversation at some previous convention or conference on using mass augmentation. So just very briefly, this has been touched on before. The gravity tractor uses electric propulsion on a spacecraft to tug an asteroid by using the gravitational attraction between the spacecraft and the asteroid as the tow rope. Now, as has been alluded to before, the biggest problem with this is that you're very limited in the force you can apply if you're limited to a few tons of spacecraft mass. I'm not sure anybody talked about this numerically, so let me be more specific. If you're moving something like a 100-meter class asteroid with a spacecraft that's something like 10 tons, which is what ARM roughly weighs, you get something like 20 millinewtons of force. That's the most you can apply. It depends on the radius and the size of the spacecraft. To put that in perspective, that's about 1% of the maximum thrust that the ARM spacecraft has. So even though we think of SEP as being low thrust, this is 2 orders of magnitude lower than that. To put this in a slightly more intuitive, graspable sense, let me describe this in more everyday terms. What we're trying to do is move a chunk of rock the size of a large office building with a spacecraft that looks roughly like a large wrecker tow truck they used to move semis, pulling on it with a single human hair. Turns out a human hair has about 20 millinewtons of tensile strength. And in fact, the experts in human hair tensile strength are the cosmetics industry. So when I look this up, I can tell you that this is more like a bleached human hair, which has slightly lower tensile strength because it's been damaged. So that gives you a sense of the challenge. Now, the good news is this is space with no aerodynamic drag and other limitations. So given enough time, you actually can tow an office building size asteroid with a human hair, but it would sure be nice to be able to do it faster. So as Tim and others have alluded to, if you can grab material from the asteroid, you can amplify the upper limit on your towing capability. And for something on the order of 1,000-ton sample collection, which was roughly what the ARM spacecraft was sized for, you can get into the few newtons range. So that's roughly what the ARM spacecraft is designed for with SEP. Now, this still has the advantage that you can tug the asteroid in pretty much any direction you want. It has the disadvantage that unlike a traditional gravity tractor, you do have to have a kind of mechanical interaction with the asteroid. So you care about what its surface properties are like and whether there is loose material on it. In fact, it requires that there be some material that you can pick up. So this is one of the potential limitations. So how does the math work out? Several people have talked about a kind of intuitive gravity tractor where you just hover the spacecraft directly over the asteroid. It turns out that perhaps a better way to do this is to actually have the spacecraft orbiting the asteroid but offset from the center. And one attraction of that is that if you stop thrusting, you don't fall down and crash into the asteroid. You stay in an orbit around it, and I'll show you that in a minute. So in one of these displaced orbits, if we have a 1,000-ton sample mass that we've picked off with a 10-ton spacecraft, and we have a 100-meter asteroid that's, in this case, on the order of 2 million tons, the maximum thrust you can apply is about 2 newtons, which is pretty much in line with the capabilities of the armed spacecraft. And with the ISPs typical of Hall thrusters, you need several hundred kilograms of propellant and only a few months of thrusting to be able to move that asteroid by a centimeter per second. So it's feasible to do this without blowing the propellant budget for the mission and without adding years to the mission duration. So the theory here would be that if you decide to do an armed demonstration of the pick a rock off a large asteroid approach, then you have the option of doing this demonstration. I'm not trying to pick sides in the debate about whether it's better to do a mission that grabs only a small asteroid or to do the demonstration that visits a large asteroid and grabs a boulder. But if you choose to do the latter, you have the option of demonstrating a very real asteroid deflection capability. So we put together a little trajectory simulation. Let's see if I can make it play. There we go. So this is an asteroid. Can we dim the lights a little bit? There we go. So we have our asteroid, which is moving in the upper left in this picture. So there's its velocity vector. And what we want to do is basically add to its velocity vector. One of the easiest ways to change its position is to accelerate it in the direction it's already going. So the spacecraft is thrusting. You can see our feeble attempt to have a picture of an ion plume there in the blue line. That thrust is pushing the asteroid orbit ahead of the actual asteroid position, and that imparts an average acceleration through gravity to the asteroid in the correct direction. So we simulated this for something like 150 days without crashing into the asteroid. We've got the solar arrays pointed at the sun at the appropriate times. And one of the other attractions of this approach is that you are allowed to point the thrusters actually in the direction you want to go and not canting them off at a 45-degree angle to avoid pluming the asteroid because you're not pointed directly at the asteroid. Now you'll notice that this trajectory is kind of looks sort of random. It's a little bit loopy. That's partly because the asteroid has an irregular gravity field, but mainly because we didn't take the time to do a smarter job of designing the trajectory in a way that would be more stable. And here's what happens. You'll notice we've turned off the plume, so that plume went away. If you lose thrust, you go into a stable orbit around the asteroid. Oops, start it over again. So that it doesn't crash into the asteroid. Now, one of the other attractions of the mass augmentation, because you can increase the force you can apply by a factor of 100 or 1,000, is that you can either use that amplification to move the asteroid a whole lot faster, or you can use that increased force to allow a much greater offset distance from the asteroid. So operating relatively dumb spacecraft around an irregular rotating body with a lumpy gravitational field is sort of nerve-wracking if you're trying to do it up close. Being able to do it at a greater distance may simplify the mission operations and reduce risk quite a bit. So we laid in a kind of a notional timeline for this demonstration based on the timeline that's being developed right now for the OSIRIS-REx mission. And we concluded that you could probably do this demonstration, including the part about picking up the material off the asteroid, in a little over a year. So it should be feasible to fit that within the nominal mission plan. Let's see. So the next question we wondered was, well, is this a useful demonstration to do? And in particular, how much can you scale this up? Or another way to phrase it is, what's the biggest asteroid that you could move with this approach? Given roughly the design specifications of the ARM spacecraft, which is that you've got several tons of propellant, it depends on how much you use getting to the asteroid, obviously. We sort of concluded that you could apply a 1 centimeter per second delta V to an asteroid up to about 200 to 350 meters in size. So that's not quite the top end of the largest possible threatening asteroid, but it's pretty close. Now, one caveat to this, that assumes that the asteroid that is dangerous is in an orbit which is easy enough to get to that you can use any rendezvous-based technique in the first place. If the threat is an asteroid in a very elliptical orbit that is
Amber alert going off for everybody.
That is has a high relative velocity relative to the Earth, then you need an intercept technique, and this doesn't work. But at least for asteroids which are reasonably accessible, it's a viable technique. And it turns out, even though the accessible asteroids are a small fraction of the total population, they're a relatively large fraction of the risky population, precisely because they come very close to Earth so often. So with that, I will take any questions you've got.
Okay, thanks, Josh. Do we have any questions in the room? Come on up to the mic, please.
Is it the gravitational pull of the asteroid that keeps you from moving away from it?
Yes.
Okay.
So that's why it sets the limit, and it's also why the tow truck analogy is a good one. If you apply a force that exceeds that gravitational force, you break the rope and you go much farther away from the asteroid.
So what is the total thrust of the spacecraft in your demonstration now?
I think we attempted to use the ARM reference design, which is something like 2 newtons.
2 newtons.
And that's just the SEP thrust. Obviously, there's chemical thrusters for RCS that are...
So basically, it seems like there's a design, and this is not so much for the demonstration mission, but it seems like there's a design choice when you start talking about moving 1,000 tons of material of, well, what is more likely to have problems? Moving 1,000 tons of material to get, well, I think it was 1.89 newtons or something like that,
right,
or just putting the spacecraft against the body and thrusting it directly to get 2 newtons of thrust. And so it seems like that needs some consideration, that it's not obvious to me that, if you sort of like, if you had to do this, if you're saying, the Earth is going to get hit by this thing, we have so much time, we have to do this, it has to work. It's not obvious that moving the 1,000 tons is the safer option there.
I agree, it's not obvious what the best deflection approach is, and it depends a great deal on the properties of the asteroid that ends up being the dangerous one. But one of the reasons for doing this rather than a direct push is that you're not limited in the direction you want to push it. So if, for example, you are trying to deflect a 100-meter asteroid that does not have principal axis rotation, even if it does have principal axis rotation, you probably, it's difficult to de-spin it, right? So you may be limited to pushing it in a direction aligned with the poles. And if it doesn't have principal axis rotation, then you have a problem of even getting consistent.
Yeah, I understand that. Just as an aside, and for the record, sort of some of these other talks have talked about spacecraft with 80 newtons of thrust using solar electric propulsion, and so
that was
chemical. That was chemical. Okay, but still, and some of them have talked about more than that, a couple of newtons, and so you could.
Right.
Yes, it's all a question of solar cells, right? I mean, you get bigger solar cells, and you have more thrust. I mean, so in other words, it scales better, it seems like, than the moving the mass onto the space.
Sorry, which scales better?
Putting in bigger solar panels to have more direct thrust scales better, because we know how to do bigger solar panels, they're easy to do, than to say, well, we'll move 2,000 tons,
It's not obvious to me that a solar array that can provide tens of newtons of SEP thrust is easy when attached to an asteroid.
Fair enough.
If for no other, the simplest reason it's hard is that it's going to be dark half the time, which may coincide with the direction you want to push. But yeah, I'm not saying it can't be done, but it's not obvious that it's easy. Any other questions or comments?
Thank you, Josh. Okay. John.
Okay, our next speaker is John Brophy. John is a JPL fellow and is a specialist in electric propulsion for the Jet Propulsion Laboratory, and he's been there since 1985. He's responsible for the ion propulsion system for NASA's Dawn mission, and has recently was a co-lead on the Keck-sponsored asteroid retrieval mission feasibility study.
All right, thanks. Okay, so we're going to talk about a little bit different approach. I think you heard about this earlier in this session, which we now call an ion beam deflection or ion beam deflector. When we originally wrote this up, we called it push me, pull you. Nobody liked that, so we changed the name. But there are other names. This came out of, first time we heard of this concept was from Kitamura, who looked at it for dealing with orbital debris. And so you blast, you have your SEP vehicle, you blast the ion beam into it. You don't need to grab the thing, you don't need to detumble it. But you do need to thrust in the opposite direction in order to maintain your position relative to the object. And then Bombardelli and company said, well, let's apply this to deflecting asteroids. So same idea, you blast the ion beam into the asteroid and thrust in the other direction to maintain the position. The attractive feature of this is that now the coupling force that holds you relative to the asteroid is entirely within your engineering control. It decouples this from the size and spin state of the object that you're trying to move. And so if you scale the vehicle to much higher powers, you can take advantage of all of that additional thrust, or at least half of it, and use that to deflect the asteroid. The other interesting thing is that you can think of this basically as a kinetic impactor, where you're impacting it at an atomic level, but with potentially, with an arm-sized vehicle, a few thousand kilograms of stuff. So it's a kinetic impactor with impact velocities of 30 kilometers per second or more, and a few thousand kilograms of mass. So it's very much like the kinetic impactor. So anyway, this might push me, pull you, because you're going in both directions. Okay, so the question is, well, does it work? Do you really get that force applied to the asteroid? Well, this occurred to people for other reasons, and they take a plate here, graphite disc, and stick it into the exhaust plume here of a Hall thruster. Hall thruster's on a thrust stand, and this is also on a thrust balance. And so it turns out that those two match to within a few percent. So we know that if you hit the asteroid with the ion beam, you will indeed impart the right thrust to it. There are some real-world effects, of course. Some of them is that not all the exhaust might hit the asteroid, but you can control that in terms of how you engineer the thruster, how far you are from the asteroid, and how big it is. You will sputter the surface of the asteroid. This is like sandblasting at an atomic scale. But if the spacecraft's far enough away from the asteroid, it won't affect the spacecraft. And the amount of impulse you get from the sputtered products is negligible, even though it would help. You don't get a lot of elastic collisions, and you won't charge up the asteroid because the ion plume has lots and lots of electrons and ions. Hall thrusters are really good for moving heavy things, but it turns out gridded ion engines are really ideally suited for this ion beam deflector, and that's because you can make them with almost no beam divergence. So here's an actual photograph of this Nexus ion engine. It's a 20 kilowatt device, an ion exhaust velocity of 70 kilometers per second. So now we're talking some real speeds here. You can get an idea how big it is. This is Dan Goebel here. I'm not sure who photobombed the picture here. But it has flat carbon-carbon grids, which allows you to get this really very low beam divergence of only a few degrees. And it'll last for a very long time. They did test it for over 1,000 hours, but had very low erosion. And so 20 kilowatts, that's like half the ARM vehicle power level. So you've heard a lot about these things, gravity tractor and kinetic impactor. Kinetic impactors typically look at impact velocities of 5 to 25 kilometers per second or so. It depends on how you do the terminal navigation and guidance. And maybe several thousand, a few thousand to several thousand kilograms. And as an earlier talk said, with just a plain gravity tractor and our 100-meter asteroid, you're down less than 100 millinewtons for a 10-ton spacecraft. If you take the ARM-sized vehicle and you can deliver 10 tons of propellant and spacecraft to the asteroid, 6,000 kilograms of which is propellant at 30 kilometers per second, as I said, that's very comparable to a kinetic impactor in terms of mass and velocity. And you can direct it right along the velocity vector, which is the most effective way to deflect it. So if we now look at how much force can we apply to the asteroid as a function of the asteroid diameter, we see that it's basically a straight line. That is, it's independent of the asteroid size because it's entirely within our engineering control. So that's a nice feature. And it is an order of magnitude or more greater depending on the asteroid size. Even if you pick up a rock, a 20-ton rock, it still provides significantly higher coupling force until you get to really big asteroids. But if you don't like this thrust level, you can just re-engineer it, but go to higher power levels, higher thrust levels. The other nice thing is that with a very collimated beam, say a 5-degree beam divergence, if you want to deflect say an Itokawa-sized asteroid, you could be a kilometer away from it, and all of the beam would hit it if it were spherical. It's not, so you're going to have to be closer. But if it were spherical, you could be a kilometer away from this. So you have a safe distance from the asteroid. You don't have to worry about backsputtered material. And we know we can build ion thrusters to do that. So we looked at how does this compare to kinetic impactors. So if we have kinetic impactor masses of 1 to say 5 tons here at different impact velocities, and compare that to an ion beam deflector that has 5 tons of propellant delivered to the target, of which half is impacted on the asteroid at these different ISPs, or think exhaust velocities, you multiply it by 10. And you can see you can get really much higher total impulses delivered. It takes time to do that. It doesn't happen instantaneously, so that's the trade-off. And of course, time is the key. One of the things that we know for sure, probably for sure, that if you have a potentially hazardous object, you're going to wait as long as possible before you do anything about it, right? So the question is, how long can you wait, or what's the minimum time you have to get there in order to deflect it? So Dan Grebo and company looked at this asteroid 2011 AG5, which you just heard about, and looked at how to deflect it with a kinetic impactor. So we had them redo that analysis using this ion beam deflector. They were trying to get 10 Earth radii deflections on the B-plane prior to the keyhole passage. The reason for 10 Earth radii was to knock it not only away from that keyhole, but other potential other keyholes. We could do the same thing, 10 Earth radii with this ion beam deflector at 80 kilowatts in 3,000 seconds. It would take 4 tons of xenon, but it would take about 1 3/4 years instead of about the 1-year lead time that the kinetic impactor did. But you may not need 10 Earth radii if you have very precise control of what you're doing. You might need only a couple. And at 2 Earth radii, you could now do this at 40 kilowatts, and it would only take you a couple of tons of xenon. And maybe a 1.5 years lead time once you got to the asteroid. The other interesting thing that you might be able to do with this, and I know there's a question earlier, is that if you didn't line up the center of pressure with the center of mass of the object, you could affect its spin state. And if you were smart about this, you could slow down its spin rate. So if you go to an asteroid that you want to capture, it's possible that you could, as Andy Thomas suggested, use this approach to slow down the spin rate of the asteroid, making its subsequent capture easier. And the pressure that this ion beam puts on the asteroid is well below the 25 pascals that you heard about earlier from Dan Shears. So it won't disrupt the body because it's a very gentle activity. And it takes a manageable amount of propellant to do this, even if it's 1,000 tons spinning at 2 RPM. So to sum up, this is a potentially very attractive approach. It's like the gravity tractor because you don't have to de-spin the object, but it's unlike the gravity tractor because you can get a much higher coupling force, and a coupling force that's completely within your engineering control. You could test this as part of the baseline asteroid redirect mission. Even if you did nothing, you could just point the Hall thrusters at the asteroid and blast into it. Or it could lend itself to an international cooperation where someone provides a gridded ion engine with a very low beam divergence and do that as part of the demonstration. The total impulse and thrust are, as I said, entirely within our control. That total impulse is potentially competitive with kinetic impactors. It also saves you on the fact that after you're done blasting into this thing, you still have the spacecraft there, and you can get a very precise measurement of what you've done to the spacecraft. In fact, you get that as you go along. And we know we can build gridded ion engines which would have the right power level, very high exhaust velocities, and very low beam divergence angles. Thank you very much.
Okay, do we have any questions from the audience? Any?
I've got one question here. John, good talk. On just a question on the chart where you showed the gravity tractor, you showed a log-log plot, and you had a 20-ton boulder. I don't know if you could flip back to that real quick. Yeah, that one right there. So obviously, depending on the mass of the rock that you pick up, that keeps offsetting that.
Right.
But I'm still not completely sure I understand that inflection point. If you could explain why on a log-log plot that slope changes there.
Yeah, so it's not obvious because, like anytime you do these analyses, it's chock full of assumptions, right? So the assumption here was we were trying to make the gravity tractor look as high a coupling force as we could. And so we were trying to get as close to the asteroid as possible. So we were assuming you were canting the thrusters at 60 degrees to fire past. This is not an orbiting gravity tractor, but just a regular.
Okay, this is an offset.
So once you get to about this mass, you now exceed the half of the thrust, and so you're no longer canted at, you're canted at less than 60 degrees, and so the amount of thrust available to counteract the gravity forces goes up.
So that could be eliminated by going to the halo approach.
Yes, that would change that.
Okay. Great, thanks. Any questions, Dan?
Actually, I had a question for Paul Abel. Scientifically, bombarding a surface of an asteroid with ions, would that sort of mess things up in terms of scientific interpretation?
Yes, it would.
Okay, I was just from a science standpoint.
Yeah, you're just, this is a surface effect.
That's exact. The surface is the most important part scientifically. So you ruin the surface.
So with the gravity tractor, what separation were you assuming that the spacecraft and the asteroid were separated?
So with the gravity tractor, that varies as a function of the asteroid diameter. So in fact, if you look here, so this is the height above the surface for the gravity tractor. So it varies.
Okay, is it a certain number of diameters of the asteroid then?
You could recalculate that.
Okay, that would be an interesting number.
It's a radius because you're at 200 there, and if you go across, you're at 100.
Yeah, and this is the height above the surface. Assumes spherical asteroids.
Yeah. So he's basically at a radii.
Okay, thank you.
And that's a good segue into my question. You assumed a spherical asteroid. How much do you think the fact that the asteroid is probably not spherical, has concavities and such, would decrease the efficiency of this?
Yeah, so most likely what that would do is require you to be closer to it, because the if it's hot dog shaped or something, you want the ion beam to impinge on the full, you don't want it to miss, and so you got to be a little bit closer. But the fact that it has a non-uniform surface doesn't matter, because this is an atomic process. So the surface roughness is independent of the force that gets applied.
Well, but I'm thinking. Well, I'm not thinking about bouncing. I'm thinking about it impinging a concavity, so that there is, the push isn't all normal. Yeah.
Oh, yeah. So everything on an atomic scale looks the same. So it doesn't. Unless you bounce off, you got momentum in this way, and that momentum is going to get stopped, and so it'll push it that way. You get some sputtered products, but those come off at such a low velocity that it won't. It would help you, but it's negligible, and unless it's an elastic collision, you don't have that effect.
Yeah, I think it deserves some looking at.
Okay.
All right. Any other questions? Nobody online? Okay. All right.
Thank you, John.
Thank you.
All right, so at this point, first of all, I'd like to compliment all the presenters on being spot on time. And probably shouldn't have said that till we're done, but we're going to we've got a break here for 15 minutes. I'm sorry, 10 minutes. So back at 3:50, and we'll have the final 4 presentations and then the discussion.
That was like 2 seconds. It's like I waited.
Yeah.
No, I don't think it's well, sure. And even if we're 50%, it's better than that's what it's here. But no, I think
Test 1 2 3. Test 1 2 3. Test 1 2 3. Test 1 2 3. Test. Test.
Test 1 2 3. Test 1 2 3. Test 1 test 1 2 3. Test 1 2 3 4 5 6 7 8 9 1 2 3. Test 1 2 3 4 5 6 7 8 9. Test 1 2 3.
It's like we applauded and 15 seconds later we said thank you.
Bag and scratch with the fingernail.
All right, I'm gonna hang out here for a while.
Okay. And Don built a homemade finger grab.